Hello everyone and welcome back to the channel. For those of you who were watching last week's video as well, unfortunately I did not get the job offer to be a back-end developer from my girlfriend. She told me that she's on a bit of a hiring freeze at the moment and then proceeded to give me 2 lead code hards in 30 minutes, which I was not able to do. Nonetheless, here we are, keeping my head high for this week's video, which is about caching at Facebook. So let's go ahead and get into it. Alrighty, as per usual, we're going to go ahead and freeball this one because I simply do not remember what I've written down on the page, but I think I'm just going to make it up as we go. So today we are talking about the Memcache paper, which is out of Facebook in 2013. So it's worth noting that I've actually made a video on Tau, which is a different Facebook paper on this channel, and the two of these papers in many ways share a lot of similarities. Tau is ultimately Facebook's graph database that does a ton of caching, and Memcache is basically just a separate individual caching layer, and they share a lot in common. Tau tries to build upon the Memcache work and improve upon it, but this ultimately lays the foundation for that one. So if you haven't seen the Tau video, that would be a solid follow-up to this one. Anyways, let's go ahead and get into the background of this paper. Basically, the paper name is Memcache. There's also this technology called Memcached, which is basically an open source single server cache, right? So it's basically just running a hash map on a server, and entries can get expired over time. So basically the reason that Facebook needs these is because when you're loading a Facebook page, they may end up making 500 different API requests to a bunch of different servers and loading results from all these places, and this level of fan out is not really acceptable to go to normal databases. So ideally you want to be keeping a bunch of data in memory, or at least as much as possible, especially for popular results, so you can get data back as fast as possible. It's also good because if you just have a bunch of servers hitting a bunch of databases at the same time, you're going to be putting too much stress on them and they can go down. So again, in the same way, caches, because they can handle all these requests much faster, are basically shielding databases from the load of the system. What's also really nice about a caching layer is that you've got a bunch of different heterogeneous data sources, right? So they may have databases, they may be reading from Hadoop, and being able to just have one unified cache layer, as opposed to coupling it with each of those database storage tiers, is that it can work with any particular storage system that's keeping data on disk, and then it can store things separately. Or it can even store things that aren't necessarily even being cached. It could be storing the result of some batch computation or something like that. So again, the really nice thing about this is that we get this separate scaling piece, right? Like it's not tied to the number of database servers I have, it's more so tied to the actual read load of the system. Obviously, keeping things in memory is going to increase our read speeds, and then of course, like I mentioned, we're shielding our storage tier. So again, what they call their system here is just Memcache, right? So Memcached is a single server, and then when they say Memcache in the paper, it's referring to the distributed system that they built. All right. So at a very, very high level, basically what we're doing here is just a bunch of look-aside caching, right? So you've got all these clients, so even though I draw it as a person, in reality it's probably just some sort of application server. And the application server is going to make a read from some cache. Ideally, you get a cache hit, but if you don't and we miss, then okay, we're going to go ahead and read from the database. And once we get that data from the database, the client itself is actually responsible for setting the key in the cache. So we're going to discuss some complications that arise from that in a little bit. Same idea here, except a little bit different on writes, is that if we're a client, which again, not a person, really just an application backend server, ideally we're going to go ahead and set some key in a MySQL database, and then the database itself is going to go ahead and invalidate the cache. We'll talk about why the database is doing that. There's a reason for it as opposed to the client, because in theory the client could do the invalidation, and that's how they draw it in the beginning of the paper, but then ultimately it turns out it's the DB that does it. Another question is, okay, rather than invalidating the cache, why don't we just actually set the value of the key itself? Well, we could do that, but what if 2 clients were writing at the same time? And now you have some sort of race condition between who is actually going to be setting the value in the cache at the same time. You can have flip-flops here, and then you get the wrong result. So invalidating is typically easier, and then the value gets set on the read path. Okay, so like I mentioned, we've got this concept of a fan-out pattern, right? So if I'm an application server, I literally might be reading from 500 memcached instances at once, and that means that we have a lot of fan out of these network requests. So a few problems of this is that if one server is super duper slow, that's going to bottleneck everyone from performing page reads, which is going to be problematic. There's also this concept of in-cache congestion, which is an interesting one. It's not a term that I've heard before. This is basically like if you've got some network switch, right, in a data center, and then maybe it's connected to all of these different Memcache servers. If there are too many packets going into the network switch at a time, things may get dropped or things may get slow, and that's going to be problematic as well. And then finally, if I am basically, a web server right here, and I've got a bunch of different cache servers over down here, now I may have to be maintaining a connection to each cache server. And not only am I doing that, but I may be having to maintain a connection to each cache server on every single thread on this web server. So if there were 100 of these, now all of a sudden I have 300 connections, and we don't want to maintain those. Okay, so how are we going to improve those issues? Well, first let's talk about the high-level overview of Memcache. Basically, we've got a bunch of caches, and we're splitting them up with consistent hashing, and then we've got this fan-out pattern right here, because everyone's pretty much reading from every cache as it's relevant to them. So note that this is kind of acting as if we're doing key ranges. In reality, this is going to be the range of the hash of keys. That's how consistent hashing is going to work. So these would be our web servers or our clients, and these are going to be the caches. Okay, we're going to now get into a few performance optimizations. This is where things are going to get a little bit deeper, and we're going to try and solve some of the problems that we mentioned before. Basically, for one, if all of these web servers are fetching results from every single one of these caches, and they're fetching a lot of keys at a time, ideally we want to batch as many requests as we can at a time to limit the actual overhead of sending all these requests to cache instances. So not only should we be fetching these keys in batch, but we should also be doing so in parallel, right? It would be stupid if we went to one cache, got all the data, then went to another cache, got all the data, then went to another one. We should be doing that in parallel. Another thing that I mentioned was kind of the threading issue, right? If you have 100 threads running on a server, you don't want to have 100 times the number of cache servers open connections. That would really bog down the server. So instead, each one of those client servers is going to be running a single MC router process, where the MC router process is the only one that's responsible for connecting to Memcached instances. Or separately, another option is you could be running MC router, that process embedded on some sort of proxy server, and then that way, rather than maintaining a connection to every single Memcache server, you just maintain one connection to the proxy. So that's possible as well. Finally, for reads, they actually end up using UDP as opposed to TCP, which is an interesting one. The reason they do that is because UDP is just going to have less information embedded in each packet, and also you don't necessarily have to establish a handshake to get data from a server. You just go ahead and send a packet over there. And so UDP is nice performance-wise, but it also has some complications associated with it, which is that you can have dropped packets, right? There's not really an automatic retry mechanism, or packets can even come out of order. And so if that does happen, basically how the client treats this is, hey, I just had a cache miss. That being said, one of the reasons that you may see things like drop packets or out of order packets is because the server that you're trying to hit or the cache that you're trying to hit is overloaded and is not in a good state right now. So there's extra logic basically that if you dropped packets and that's why you had a cache miss, and then you do a read to the database, don't actually try and backfill that value in the cache. Just avoid that altogether. That being said, for set and delete operations, right, because we invalidate keys in the cache and we also set a key in a cache after we read from the database, we actually do that with TCP, the reason being that we want some sort of auto retry mechanism. In theory, you could just do that on top of UDP, but there's not really any good reason to do so. So this is going to be nice for retrying our failed operations. And then finally, we're actually going to be performing some amount of flow control. So we do flow control in TCP as well, but TCP flow control is based on basically the capacity of one connection, right? So the way flow control generally works is you have some window. You're basically saying, here are all my open connections, my open requests. Oh, my request just got a response. Now I only have 3 open requests, so I can actually get another one in there because maybe my limit is 4. So same concept, and we're doing this in the MC router, but rather than doing this at the level of sending requests to one single Memcached instance, we do it for all cumulative requests to Memcached instances because we have so much fan out that ideally you want all of the clients ensuring that they're not sending too many requests all over the place. So that's a really nice thing to do, and you just do that using a sliding window. Finally, like TCP, this is kind of doing an additive increase and multiplicative decrease. So as you continue to get successful requests, you can very slowly increase the size of that sliding window. And then if for whatever reason you drop packets or a request doesn't get a response to it, you very quickly decrease the size of that sliding window, and that's to make sure that we don't overload our cache fleet. Okay, so now I'm going to describe a couple of problems that also come up in a system like this, and then we're going to talk about how we actually solve them. So the first is called a stale set. So it's a pretty simple system. Basically, the idea here is, okay, let's say I've got one client on the left who's a reader and one client on the right who is a writer. Basically, the reader is going to attempt to read from the cache. Maybe the value is not there for whatever reason, so we have a cache miss. And we know that when we have a cache miss, we go to the database, we read from the database, and then we backfill the value into the cache. However, as we're reading from the database, the writing client is actually going to set a new value from that key, which, as we know, leads to invalidating the value of that key in the cache. So that's over here in step 4. This is a race condition, right? So finally, in step 5, the client who's doing the read actually sets the old value of the key X into the cache, and now all of a sudden we're reading stale data, right? So that's a race condition. We don't want that happening. The other thing that could possibly happen here is this concept of a thundering herd, where basically we end up getting a bunch of additional load on a database where we shouldn't. So in this scenario, basically we've got a writing client over here, and then we've got a bunch of guys on the left who are doing reading. And basically the writer is going to make a write, which as we know is going to invalidate the key in the cache. And then from there, we've got a bunch of readers who concurrently at the same time are all going to read from the cache. And because they're all reading at the same time, the cache has not actually gotten a value filled in yet for it. And so now all of those requests are going to be cache misses, and then they're all going to go over here to the database. And this is particularly going to be a problem with popular keys. So because all of these readers are reading concurrently, all of a sudden our database gets a bunch of extra load that can cause it to fail, and then we may even have cascading failures just due to rebalancing or something like that. So you want to avoid both of these problems. So the mechanism that we use in Memcache to do so is something known as a lease. So a lease, very simply put, is basically like a compare and set, and the cache is going to return it. But let's go ahead and describe it. So again, over here we've got one reader. Over here we've got another reader, and over here we've got a writer. So let's imagine to start the lease token is ABC, right? So the reason the lease token is ABC is because this reader comes in, it does a cache miss, and so now right after the cache miss happens, the cache says, okay, for the key that you cared about, I'm setting a token called ABC. So that's going to be our lease right there. And we're going to return ABC back to the reader. Now, another couple of nice things happen as a result of this. Let's imagine that because this was a cache miss, there's no value currently in the cache, right? So it's possible that we may have one of those thundering herd scenarios where another reader also comes in and tries to read the same key, and it's not present. So normally, this would result in a read to the database, right? Or rather, sorry, not like that, but a read from this guy to the database. And we don't want that happening. We want them to eventually just read the value from the cache. So if they read from the cache and they see that there's an active token for this key, what they're actually going to do is just go ahead and wait a couple of seconds. Now this is completely imperfect, right? Because normally you don't want to rely on like exponential backoff or anything, but in practice it actually works very nicely. Basically, if you wait a half second, you know what's probably going to happen is this reader over here is going to go fetch a value from the database and ultimately place it in there. So that works a lot of the time, which is really, really nice. So that's one aspect of the lease, is basically preventing others from reading at the same time as you from the database, thus preventing thundering herds. But another really nice aspect of it is also preventing stateful sets, because as we mentioned, what could happen is this reader could actually go ahead and read and try and set the value over here after that key has already been invalidated. Because in step 5 we have a writer. The writer is going to write to the database. In step 6 we invalidate the key in the database, which at the same time is going to say, ooh, there was a token ABC here. Let's go ahead and remove it. That's no longer valid. The reason why we remove it is because when this reader ultimately reads from the database a stale value and tries and come in and say, hey, I'm using token ABC to set a new value, the cache is going to say, oh, wait a second, token ABC is no longer valid because I've had my key since invalidated, and so I no longer am going to accept your write. So this way, this guy can go ahead and retry over here. He can do another cache miss and then go to the database and then, fill in the proper value accordingly. Great. Another concept that we have is going to be that of Memcache pools. So basically, empirically, after running these Memcache instances for a while, the developers at Facebook found that data has different properties, right? So keys and values can have different sizes. They can have different churn, where churn basically is implying how often things are being evicted from the cache or no longer relevant. Or they can have different access rates. Certain data is being accessed really frequently. Certain data is being accessed very infrequently. And so ideally, what you want to do is store data in the same Memcache pool, which is basically just a set of Memcache servers that have similar properties. Because if you don't, you can have certain bad scenarios that come about from different access patterns. So one example that they gave was this concept of low churn keys, right? So a low churn key is one that's rarely being evicted from the cache, or in theory shouldn't be evicted from the cache because it's always being asked for. But sometimes if it's paired with a bunch of keys that are briefly very, very popular, so for example, like a recent post or something, but very quickly will become unpopular, it's possible that if we run out of space in the cache, because the high churn keys were very recently being accessed a lot, the low churn ones may get replaced by the LRU policy, and then all of a sudden we've got a bunch of high churn keys in the cache and they're no longer being accessed anymore anyway, so that would be wasteful. So separating these guys into different Memcache pools can have nice properties as well. Sorry, I'm noticing that sometimes when I do like a little PowerPoint thing, it gets messed up a little bit, so I just went ahead and fixed that. But the idea here now is that in addition to having a bunch of different pools, we may also perform some cache replication. That being said, normally in Memcache, we try and rely only on using partitioning to partition the data set. That being said, we'll also do replication in certain unique scenarios. So one scenario that we'll do replication for is basically when we have a very, very small key set that's very frequently accessed, right? So let's say we've got 100 keys in our key set and, fairly small values such that the entire thing can live on a single node. But it's just a super popular key set, and so you've maybe got hundreds or thousands of client servers that are reaching out to it all the time. In this case, there's going to be a ton of load on that server, and it would be great if we could go ahead and distribute that a bit. In theory, you could partition the key set, but the requests themselves individually are not very expensive. It's more so that there are just a lot of them. So partitioning it is not really going to make a big difference because the actual overhead of returning the data was never that big in the first place. So instead, what you're better off doing is literally just setting up a replica of the same data set, and now each of them are going to have half the number of requests, which is going to be a lot better. It's worth noting that if it comes to choosing replicas, clients are basically just going to randomly load balance based on their own IP address. Another concept that we have in Memcache is going to be this idea of gutter servers. So typically in the past, with a lot of the distributed systems that we're talking about, if servers go down, what we'll try and do is generally rebalance the keys between them, right? Which is something that is not exactly trivial, but ultimately, if it's something like a database, you have no choice, right? The data's got to live somewhere. But the nice thing about this stuff is that at the end of the day, it's cache data, and so it doesn't have to be perfect when you rebalance. Basically, rehashing or rebalancing is also going to be very hard because certain keys can be considered hot, right? So if there's 10 keys that get a ton of load, right, maybe up to 20% of the load of a single server is the value that they use in the paper, actually taking that key and then just putting it on a random new server can cause that server to get overloaded, crash, and now you have cascading failures. So instead, they have this concept of gutter servers, where a gutter server, like this one over here, or gutter servers in general, are only responsible for like 1% of the servers in the total cluster. But basically, if this guy goes down over here, what we'll first try and do is make a request to it, and if that fails, we'll go ahead and request to see if the value exists in a gutter server, and if it doesn't, obviously we're going to pull it in from some sort of database. So in this way, any other client is going to do the same exact thing, right? It's going to make that same request, and then it's going to hash that request to the same gutter server in the gutter pool. So ideally, you'll still be able to get that key, and it's going to resolve a lot of the cache misses that would have happened otherwise and save a lot of load from our database. It's also worth noting that, the database doesn't necessarily know that this gutter server actually has cache data on it, or it doesn't know where the cache data for the keys actually lives because now we've kind of broken our consistent hashing policy. And so as a result of that, we basically want the data on gutter servers to expire fairly quickly, and so we do. It's fairly short-lived, and it'll basically auto-expire. Cool. Let's go ahead and talk about this concept of regions and clusters, because these are two keywords that we're going to need to get through the rest of this paper. Number one is a cluster. So this is basically just a combination of Memcache servers, also a bunch of client servers, ideally co-located in the same data center, so probably going to be the same failure domains as well in terms of power or network or stuff like that. Then you also have a bunch of regions, where a region is comprised of multiple clusters, as well as probably one shared storage layer, where geographically they're in a similar location, so still fairly close to one another, but still different failure domains, right? So different, probably different physical buildings or different network racks or something like that. And then there's also this concept of a regional pool, because at the end of the day, within different clusters, right, you're effectively replicating the cache data because you have different clients using different clusters. A regional pool is basically you have different clients, except they're all using Memcache servers that span multiple, like data centers or something like that. And so because, consistent hashing is going to deterministically place a key on one server, what this means is that we're doing less redundant replication of the data. Basically, the cost of this is that even though we're doing less redundant replication of data, effectively we now have to actually make requests from client servers in one cluster to Memcache servers in a different data center building, and so that's going to incur some extra latency. Okay, next we've got this concept of data invalidations. So up till this point, I've kind of implied that the database is actually going to be the one that's doing the invalidation on a cache, but I haven't really explained how that process works. So one option, in theory, if I'm a client here and I'm writing a database to a database, is to make the write, and then after that go to a cache and say invalidate. But if you think about it, that's actually a bit expensive. In theory, you may have to actually go and invalidate multiple caches, and also if I'm a client, I'm just making one write at a time. So it's actually a lot more efficient, even though it's nice to just operate stateless clients and have them do things like that. What's actually more efficient is to run a daemon process, which is basically just a background process, running on the database node itself. So they run one called MC_squeal, where MC_squeal is basically just reading from the write-ahead log on the database, taking all of the new writes, converting them to invalidations, doing a bunch of batching, and then sending those out to the MC routers themselves. The reason it's nice to do batching is so that, again, there's less overhead, right? We can send more invalidations at a time, and we're not being as wasteful of our network bandwidth. The MC routers then, within each cluster, for example, will go ahead and basically, in addition, batch a bunch of requests, figure out all of the individual caches and the requests to where they go. So again, we're doing batching, we're sending multiple invalidations to a cache at a time, and then sending them there. So that way we can batch as many of these invalidations as possible. It's going to limit the number of packets that we send and the load on all of our systems out here. Another nice thing about operating MC_squeal on the write-ahead log is that if we have a client over here and it's responsible for invalidations and it goes down before the invalidation can be achieved, now there's no invalidation. That being said, MC_squeal is something that can run on a persistent write-ahead log, so replayability is going to be a lot better because the write-ahead log is ultimately kept on disk. Okay, another concept that we have here is going to be known as cold cluster warm-up. So a cold set of caches, or a cold cluster, is just a new set of caches that doesn't have any data in them yet, right? So we need to get new data in them, but the normal process of getting data in a cache involves a lot of cache misses, which is going to be very expensive and put a lot of load on our databases. So instead, what we'll do is we'll actually have this cold cache go ahead and first proxy to a bunch of warm caches. So if I'm a client like this guy and I'm performing reads, I'll read from the cold cluster. If it's a miss, then first I'll read from the warm cluster and try and get an actual hit there, and if that doesn't work out for me, then I'll go to the database, or then as the client, I'll go to the database and backfill into my cold cluster. So hopefully that all makes sense right there. However, there is ultimately one race condition that can happen here. If this is the client and we make a write, the database is going to invalidate both the cold cluster and the warm cluster for that key. However, there's a race condition, right? Maybe this invalidation, for whatever reason, takes 10 seconds. So now, if we then proceed to try and read the key after that, we're going to go over here, we're going to have a miss, we're going to go over to our warm cluster, and then we're going to read stale data because it hasn't been invalidated yet. And then we're going to load that right back into our cold cluster, and now we have stale data over there, which is going to be problematic because it's already been invalidated. So the way that this is fixed in practice is, pretty, I guess, hacky and approximate, but, they find in practice it's totally fine, which is basically if I'm the cold region, after an invalidation, I'm not going to load any data from the warm region for another 2 seconds. Instead, I'll just go ahead and grab it from the database and treat it like a normal cache miss. Okay, let's go ahead and talk about multi-region setups. So, to be expected, this is ultimately a system that needs to be able to be geo-replicated for a variety of reasons. For one, we're more resilient to disasters like hurricanes or tornadoes or something like that that's just going to take out a bunch of data centers in a region. Number two is that we can put data closer to the user, which, especially when it's coming to caching, is very important because it just continues to lower latency, which is the objective of this entire thing. And then finally, we can also just get cheaper power costs depending on the region that we put these things in, which is always very nice. Certain countries are just going to charge you less for that. Now, this is where things start really looking very similar to Tau, which is basically that you're using asynchronous MySQL replication across regions for the storage tier where you have a master region and then everyone else is a follower. And then within a region, you're always going to be reading from your local database and your local caches, with a couple of slight exceptions. Now, finally, it's worth noting that all of the cache invalidations themselves, rather than basically going from the master database straight to all of the caches in the follower regions, are actually going to first be embedded in the replication stream. So invalidations won't happen until the data is actually, until the write that causes the invalidation is actually applied on all of the replica databases. Otherwise, we could have a bunch of race conditions where we read from the database too early before that replication stream has gotten there, and then we load stale data back into the cache, which would be problematic. Okay, sorry, more weird PowerPoint glitches, which I can't seem to, hello, there we go. Basically, let's go ahead and now talk about read after write consistency. This is where things get a little bit janky, so let's go ahead and go through them. So we've got this master region, we've got a follower region. If I were a writer in the master region, I'm just gonna go ahead and write straight to the database and everything looks very normal. If I'm actually going to be a writer in the follower region, this is where things get a little bit more interesting. Basically, we do something known as a remote marker. So if I'm writing to the follower region, I'm going to add a remote marker into the cache that basically says, hey, I'm going to go ahead and write this key right now. And as we know, all writes, because this is single leader replication, have to go to the master region. So this comes over here. Now, what this means is that if I am a different client in the same region that's trying to read the value for that key, I'm going to go to the cache. I'm going to see, hey, I know this thing is being overwritten, so I can now go ahead and actually read it from the master region instead. Then finally, eventually what's going to happen is, this data is going to get replicated to our follower region, and then the database, as part of the invalidation process, is also going to remove the marker. So basically, when we have a remote marker present, it says, go and read this from the actual master region as opposed to your local follower region. So what they're doing here is they're trading latency and staleness, right? You get more latency because it takes a while to read data from the master region, but you're not getting stale data because otherwise, we would go to the cache and we would just read an old value because it hasn't been invalidated yet. Okay, let's quickly go through a few single server improvements. So, in addition to this whole distributed system that Facebook went ahead and built out, they also just made some small changes to Memcache itself in order to try and squeeze the most out of these servers, and then some of these changes were eventually open sourced as well. So basically, we've got this single-threaded implementation, and then they changed that to a fine-grained concurrent hash table. So previously, Memcache was single-threaded. They made it multi-threaded. Obviously, you're going to get performance benefits there. Another thing that they did is actually allow the hash table to expand in size as opposed to being fixed size. The reason being that you need a hash table getting bigger over time, or else if it completely fills up, your time complexity on fetches is going to get worse because you're going to have to do a bunch of probing or chaining or something like that, and you're going to approach linear time. If you make a bigger hash table, then you're able to actually get better time complexity. Another thing to note is that every single thread in the concurrent implementation has its own UDP port, which is just going to allow more concurrent connections at once. And then also they do something known as slabs. Tau did the same thing. The idea of slabs is that different values in the hash map themselves are going to have different sizes, And so you basically put each value in the slab class that corresponds to it. So, maybe there's a 1 megabyte slab class and a 2 megabyte slab class and a 4 megabyte slab class or something like that. And the idea there is to basically try and balance the eviction rates between all of those slab caches. Now, the way that they do that is effectively they try and balance the age of the oldest item, and this is going to allow them to basically mimic like a global least recently used policy across all of those slab caches and or slab classes, and it's just going to be more efficient. Finally, they're going to at least try and handle items with a small TTE better. So some items go into the cache, and they're explicitly meant to be expired after a certain amount of time. That being said, at least natively, Memcache did lazy invalidations. So, the data would still be in the hash map, and then, if you checked it and you saw that the TTE was expired, you would just go ahead and get rid of it or garbage collect it then. That being said, this was taking up a bunch of extra memory because there were a lot of these short-lived items. So basically, for short-lived items only, Facebook implemented a system where they would actually be eagerly deleted, and then everything else would be lazily garbage collected. And then the last improvement that they have helps a lot with something like rolling upgrades or restarts or something like that, where basically they use this concept of system V shared memory for all the data in Memcache. And what this means is that this memory is persistent even after the process ends and restarts. So that way, if you kill an instance of the cache and then you restart the process, you don't have to go basically have a cold cache and warm up again. You can just get your data back really quickly because it's going to be in the same memory addresses. All right, let's go ahead and conclude this one. Basically, the idea here is that, like many other systems that we're seeing recently, basically separating a bunch of individual tiers out is really nice because you can scale them independently as needed. So in this case, it's going to be your caching tier that you're scaling independently because at the end of the day, you've got a lot of requests, they're all accessing a ton of similar data, and the data itself is not that big. So caches are going to be super effective, and you don't want to have to build out a bunch of extra database instances to just run local caches there. Having a separate tier is very, very nice. You can scale it yourself. It's also just nice because tying individual caches to whatever database you're using doesn't allow you to extend that to using different data sources. Cool. As we mentioned, caching is going to get better read performance by virtue of using memory instead of disk, and also things like hash maps. And then also, it's just going to stop us from having a bunch of thundering herds on our databases. It is going to be the case that if you have 100 clients reading from a database concurrently, that's going to put a lot of load on it, but a system that can very, very quickly answer and respond to all of those requests over UDP and multi-threaded is going to make that process a lot easier and stop the database from getting a ton of load. Another thing that they do, this is more of a design philosophy on their part, is opt for simplicity, stateless components like the client, because the client is responsible for keeping the caches in sync after they do a read, and that's completely stateless, right? Like the client is not remembering anything, it's just calling a function, read the database, and then calling another function, update the cache. Now, obviously, there are all sorts of implications in terms of partial failures here, but evidently they found in practice things weren't too bad. And then finally, they only want to include features in Memcache that actively make everyone's life better. They don't want to overcomplicate things and build all these half-baked solutions that only help a percentage of the users. They basically only want to implement a change if it's going to be super impactful. Anyways, guys, I hope you enjoyed this video. My throat was given out a little bit by the end there, but that's okay. You can call me the throat goat. Maybe don't, actually. And I will see you in the next one.